What if I told you that all those famous equations in quantum physics, Schrödinger's, Dirac's, weren't just these separate flashes of genius? What if they were all baked from the exact same, surprisingly simple recipe? A universal recipe that can not only recreate all the physics we already know, but can also predict physics nobody has ever seen before. So how on earth does a recipe like that work? Let's break it down.
All right, here's our journey for today. We're going to start with a problem that's been bugging physicists for ages. Then, we'll uncover the two super simple ingredients that might just solve it. We'll use them to build what I'm calling a universal equation machine, see what it spits out, and then, this is the fun part, we're going to push it into some really strange territory, way beyond the known limits of science. You see, for the last 100 years or so, quantum mechanics has felt like this brilliant but totally chaotic cookbook. We've got all these incredible, powerful recipes, these equations, but they were all discovered using different methods, different starting points. There was no single underlying theory of quantum cooking that connected them all. I mean, just look at the history. Each of these cornerstones of physics had its own separate origin story. First, Schrödinger comes along and cooks up his equation for slower particles. Cool. But then, just a couple of years later, Dirac finds a totally different one for particles zipping around near the speed of light. Even when von Neumann came in and unified the math behind it all, that core problem didn't really go away. There was no single starting point. Each genius was following their own separate recipe.
And look, this isn't just some historical quirk. As a recent paper by Casanova and his team points out, physicists were missing a master key. They couldn't just start with the most fundamental rules of the universe, its symmetries, and systematically build these equations. It felt more like an art than a science. And that's the exact problem they decided to tackle.
So, how do you even begin to build a master recipe for all of physics? Well, this is where the new idea gets really elegant. The researchers propose that you don't need a huge, complicated shopping list. They argue that the entire quantum universe is basically governed by just two fundamental ingredients. Let's take a look.
The first ingredient is symmetry. And this is just a beautiful, profound idea in physics. It basically means that the rules of the game don't change just because you're playing in a different spot on the field or facing a different direction. The laws of physics are constant. They're consistent. This is our first non-negotiable rule.
Okay, ingredient number 2 is the famous Heisenberg Uncertainty Principle. This is that fundamental fuzziness that's just baked into the quantum world. You can know where a particle is, or you can know where it's going, but you can't know both with perfect absolute precision at the same time. And it's not a limit of our tools, it's just a fundamental property of reality itself.
So here is the breakthrough. What happens when you take these two ingredients, the universe's unchanging rules of symmetry and its built-in quantum uncertainty, and you put them together? You get what we can think of as a universal equation machine, a single, powerful mathematical framework that just takes these two inputs and churns out the laws of physics.
So, how does this machine actually work under the hood? Well, conceptually, you can think of it as a three-step process. First, you have to translate physical ideas like position or momentum into the machine's language, which is math. These things are called operators. Second, you build the machine's engine, a single master operator that holds all the symmetry rules for whatever system you're looking at. And third, you impose one simple but really powerful rule: any law of physics that comes out has to be compatible or commute with that symmetry engine. Commuting just means the order you do things in doesn't matter. Think about it. Putting on your socks and then your shoes is very different from putting on your shoes and then your socks. The order matters. But for brushing your teeth and combing your hair, the order doesn't matter. Those actions commute. This one condition forces every single equation the machine produces to be perfectly in line with the universe's fundamental symmetries.
Okay, so the machine is built. The theory sounds amazing. But the big question is, does it actually work? Can this one single framework really reproduce the greatest hits of quantum mechanics? Let's fire it up, turn the dials, and see what comes out.
And this is just brilliant. When you tell the machine to use the symmetries from Einstein's special relativity, that's the Poincare group, boom, out pop the Klein-Gordon and Dirac equations. Perfect. Now what if you tell it to use the symmetries of our slow-moving, everyday world, the Galilean group? Out come the Schrödinger and Pauli equations. I mean, it's just astonishingly successful. But what happens when you feed it a really weird set of symmetries, a set that describes a universe where the speed of light is, for all intents and purposes, 0? This is where it gets truly mind-bending. The machine doesn't just recreate the past. When you push it into this new, bizarre limit, it doesn't break down. No, it generates a recipe for a kind of physics that, quite frankly, no one has ever cooked with before.
So let's put this into perspective.
We live in a relativistic world, right? The speed of light, c, is the ultimate speed limit. But this new regime, they call it the Carolian limit, it explores a universe where c basically goes to zero. It's a world where things happen so incredibly fast that light itself seems to be standing still. It is the literal polar opposite of Einstein's universe.
And what kind of equation governs this strange new land? Well, the machine gives us an answer, the Schrödinger equation. It is a completely new mathematical structure that describes how quantum particles would behave in this bizarre, ultra-relativistic reality.
So what's it like in this Carolinian world? It's weird. In its simplest form, you can't just rotate your experiment and get the same result. Rotational symmetry is just gone. Instead of normal boosts, you get these weird ultra boosts. The relationship between energy and momentum is completely different from anything we're used to, and here's the kicker. Some physicists think particles that obey these strange laws could actually be a candidate for dark matter. The only way you can get that familiar rotational symmetry back is to demand that these particles have spin. That is a fascinating constraint.
So just think about what this means. We started with a century-old problem, this messy cookbook of brilliant but totally disconnected equations. And we found a single framework that can derive all of them from just two fundamental principles. But what's so incredible is that this framework didn't just explain the past, it actually pointed the way to a future we haven't even begun to explore. It shows that sometimes the deepest way to understand what we already know is the key to discovering what comes next, which of course leaves us with a pretty fascinating question to ponder.